Alright friends, let's get started. I will do the first part. I'm from this place in the northwest, and contrary to popular belief, we also have an engineering faculty, and that is where I spent some of my time during the past 32 years, or even more. Jan de Kok, also a colleague from there. Now, what the story is about today, and hopefully there are not too many people from NERSA here, is trying to see what we can do to keep electricity at such a level that we can keep the economy going, and maybe the lack of performance of NERSA and other role players could be noticed here and there. But of course, I'm not here because it's expected from me by the university. Part of my hidden agenda is also to introduce to you some solutions that I found as very innovative, and they are sponsoring research at my research center. And I do think for what they do, Africa is one of the best places to be. Now, I've had the opportunity for many years not only to teach rugby, but also to play it. In other words, in terms of electrical engineering, I had the opportunity to be also out there on the field and try and see what is happening outside the textbooks. So here and there I've got an idea of what you people are dealing with. Most of you probably much more equipped to have a firm opinion on some of the cases I will deal with, but I have maybe another context and approach to this, and hopefully you'll find this interesting. After me, it will be this gentleman coming in here, Herr Dr. Dresel. Nein, meine deutsche Freund von Deutschland. And he will go on. But I will first set some context in terms of what I have experienced during the past 2 decades at least, and what I think could solve some of our issues. Of course, the language of the British is not what I've been brought up and what I do use every day. So for me, it's also a privilege to share with you my ability in that language. But people, let's see. First, overview. I will quickly reflect on what power quality regulation in this country is doing. And I'm already asking the question, really, is it happening? Then we will have to see how we can compensate for that poor voltage quality. Why the industry needs, at least the industry, needs active voltage conditioning. And then I will make the case by using a case study and show you how business risk can be improved by, in this case I will focus on voltage dips. There are other aspects as well, of course, but for most of us, voltage dips are what power quality is about. Now, we can keep this also quite informal. This is not an official lecture where you will write tests afterwards, so if you feel the need, interrupt me and ask questions or give comments. People, now this power quality that we're talking about, just to reflect quickly, mostly we refer to quality of supply, because it is in fact voltage that brings the energy to our premises, and defining power quality most of the time makes use from the point of voltage. So we talk about magnitude, unbalance, harmonics, flicker, But for most of us, that is where the problem sits, the so-called voltage dips, to some extent swells, and maybe to a lesser extent transients or spikes. Some people would like to call it this family, but we don't see them every day. Reliability, obvious, no, that makes sense. The power must be on at least. And there are the standards, at least the voltage quality technical part reflected. Well, maybe we can even call it 2014. But in the Eskom Power Quality Handbook, they define power quality as such: reflecting magnitude, unbalanced, harmonics, flicker. The only difference between what I've had there and what they've included is frequency, but that we can't do anything about. And then they will rather talk about voltage continuity compared to interruptions. But people, let's see what happened in South Africa during the past few years. Starting off in 1996, that was when the first version of the NRS 048 was relatively well defined. It started application as being used as a document that we can take, assess electricity at the point where customer is connected, and then conclude to what extent that voltage is at the minimum standard suitable for that equipment to be operated as designed. That was the idea, defining such a condition. But many changes followed. For example, in the beginning they said you need limits in the number of dips per year. But think for yourself, how can that be? How can we tell the weather to not, by means of lightning, cause too many dips during this year? It's impossible to set limits from a practical point of view. And then they started to say, we will use a statistical approach, and the other parameters, for example, assess them by means of what that parameter is doing for 95% of the time. In other words, for 5% of the time, it is accepted that stuff can go wrong. Now, the wisdom that went into the formulation of the way the South Africans perceived power quality to be done was recognized internationally. Internationally, the same kind of idea started to develop, that we need those standards well defined. Equipment was getting older, lines were overloaded, equipment became more sensitive. So internationally, the same ideas were being followed. But then, I'm glad that NERSA is not here, but the idea was that they will be using such a minimum standard as part of the way they will regulate the electricity supply industry. During the year 2002, they issued a document, and this document was quite well written, and the ideas in that, they call it the Power Quality Directive. I liked it, and I thought, this is going to do it. And they referenced the NRS 048 Part 2, whether it was 1996, 2004, 2007, or what version of the document, doesn't matter. But the idea was that they will be setting some rules to how licensees do business with electricity. And one of that rules was how they will serve customers with good power quality. You see, that was the plan. But to my experience, not a lot of that really happened. And the idea was similar to water being a consumer product, and where I can read here and see if this is suitable for consumption, that if you give money, you receive kilowatt hours, that energy is suitable for your equipment. That required some definition, and we are at the mercy of Eskom, City Power, whoever is bringing your electricity. That was the idea, that they will really do it. Luckily, the people that work there do it to some extent within their budget and other constraints. But it is getting worse. There's no doubt about that. Now, so what is happening in 2019? And I think all of you will be able to quote examples of where you have not been served that well. Oh yeah, but I see I'm still using the older version of my university. Nowadays we're quite purple, but this one still works for me. Why? Voltage is not always perfect. So let's just quickly review this. I think we will agree that in power systems there's nothing too complicated. Ohm's law tells us what should happen. Now, there's a power system out there somewhere bringing to the point of common coupling some voltages, and hopefully that voltage quality is good, especially coming from the Eskom transmission system. It should be. Well, downstream we will have some loads. The way they withdraw current could affect the current in such a way that the quality is not linearly related to that voltage quality anymore. So the way they interact with a point of common coupling, for example, can have a specific character in current quality. Now, during the consumption of that current over the supply impedances, some effects will be induced, and maybe even over the impedances downstream. But the point is, the power quality realizes at that point. Those parameters that I quickly referred to, and I assume a lot of you are quite yourself some specialist in power quality, but that is the point where we, by means of NASA regulation, wanted to contain power quality to such a level that when we connect even more consumers, that everyone will be able to realize that business plan. A beautiful example that we have dealt with in this country, and there are many more, is BMW. Coming to this country, have you seen how many people, friends, think about it, do you know that drives a BMW X3? I'm not sure I have such friends. But here in Pretoria, there in Pretoria, not here in Pretoria, they produce 350 of them every day. Damn, can you think where you're going to park those X3s? I mean, it's chaos. 350 of them. And I can promise you, those Germans build that cars bloody well. It's impressive the quality that goes into those BMWs. All the effort they do to make sure that that body doesn't rust. And all that other fancy systems that's in that car that will give you a car that will last for at least 10 years without worries. It's impressive. And they're doing it in South Africa. It is really good to see it and experience it. But that business model requires, Swane, there where they connect, to give them electricity to be able to make that car in such a way. I know they use paint and fancy gearboxes and other stuff and metal, but behind that sits electricity. So you can think for yourself that business model is compromised the moment the electricity is not good. And so it goes with many, many other processes. The point is, it has got financial consequences. If the voltage quality affects the plant availability, or if it's even really bad, you can damage equipment. So the most well-known power quality concern we will be dealing with is voltage dips. So industrial processes are increasingly sensitive to them. And the idea was that at least some of the dips should be tolerated. If you look at the dip diagram, and there I'm already taking an example of a South African industry where we did some work. Then the idea was in that category, why for you that haven't dealt with this too much? The customer must not complain. Utility will say, don't waste my time about that incident. Each red dot was an event. No, because your equipment that you've installed should be fine. We can't handle all of it. Internationally, they group in such a way, most of them sitting in the so-called area of compatibility or immunity, compatibility between supply and use conditions. But those ones, for sure, if voltage drops down to nearly 40% for 1 second, something will go wrong in your plant, for sure. We must accept it. Now, that is at least where we want to deal with today. The number of those red dots going into this area in this country is increasing. But on the other hand, I can tell you from experience that equipment being used in this country is not always that immune against those variations anymore. Look at that one, 80% for about 150 milliseconds. 80% of the voltage remain, so 20% is lost for around 150 milliseconds. Some equipment could complain, we must accept. But of course, the higher voltages are also defined, as you can see there. So this area is defined as the area of compatibility, and those areas we would like to propose to you to offer you the German pharmacy that we will get to. Right, so those ones will also be dealt with at the same time by the specific piece of equipment Christian will be sharing with you later on. He's got many others. He's got a whole shelf full of medicines available. All right, so people in this case, those red dots that you see, if you count them, there are 67 of the Y-dips, 1, 9, 16 as you can see, there are 26, plus those 6 are 32. Those ones are probably the ones that will bother us. Now, you see, those ones were being measured at the cement factory over a period of 76 days, only 76 days. If you now really look at those 32 dips that are a bit worse than the Y dips, then people, it literally translates to every 2.4 days, someone in that factory will be complaining about production being interrupted. That 350 X3s, part of the Germans' business plan sitting in München, interrupted. He made his calculation of all those billions invested last year, how are they going to make more money? But now it's only 280 for the day or whatever. You can see the consequence, same to the cement here. The guy that has ordered his BMW to be delivered in 3 months, now get it in 6 months. He's getting gatvol and he buys a Mercedes or whatever. No, it's also a reputational risk in a developing year. But the cement is the same. If Lafarge can't deliver, we buy from the other customer. So every 2.4 days, something in that plant goes wrong. That is most not how to do business. Right, so what can be done? As I've said, it realizes as a business risk, profitability suffers. And the second line, I can make this statement. I know it's a bit controversial, I'm not sure, but nevertheless, power quality regulation in this country from being controlled centrally from government cannot protect South African users. We can take them to court. No, you can. The consumers have got a right. Forget about NRS and all those stories. If I buy water and I get ill, and I will be unhappy, I will complain. And if I really get sick, I will take the seller of this water. I see those Chinese here in Joburg filling them with the fire hydrants. I can take them to court. The same with electricity, because there's a physical commodity. I give money, I take the product, I want to go make money. So I've got a right. So we can, but we're going to waste our time, I think. It will not change the future. It will maybe recover damages of the past, and you want to go forward in this country. Also, on the other hand, not all root causes under the control of the local utility. You can't control lightning. You can't control the bird on the line. Die Vogel, die Scheiße. And there's an arc across the insulator. No, we can't control it. It happens. Theft of cables. But the financial condition of our national and local utilities are not that well. They can't manage the system as good as maybe in the past. So the point is, the users of electricity will have to contain the operational risk on site. You will have to take control. And we need it, not only the electrical engineer from the attack group here, we needed more managers that understand what to be done. So active voltage conditioning is an interesting solution that I'll be sharing and already sharing with you. This can be done by a parallel device or even a series device, but you see the reasonings why this can be done nowadays. And there's just an example. You get even better ones, but this is a semicron one, and I took this example because Herr Drezel was the boss of semicron in South Africa. This German lived here for a while, and he even learned to speak a little bit of Zulu. So,
Because Afrikaans, it's okay.
yeah. But now he is using those components to make solutions for industry. And this one, 3,300 volt. People, this is a lekker high voltage for a transistor. A few years ago, I would not think this. Now, this is the nominal current that you can handle all the time, 450 amps. But you can put these stuff in series and parallel. You can make really huge power application solutions by using semiconductors. And they are fast. They are really fast. So, let's look at the shunt solution. Now, people, if you have some, by means of the constant law of misery in power systems, you have some impedance somewhere, sitting upstream, the local transformer. If we take some power electronics, it can be done quite fancy, because we can emulate a reactive current. We can generate a current here that can be fully capacitive, totally a lagging current being injected here, and you can see what's going to happen. By means of manipulating the voltage drop over that supply impedance, we can compensate the adverse effect coming from the utility to the load. And now I refer mostly to trying to do it for poor regulation. In other words, the voltage over this changes too much when current changes, or when there's a sudden dip condition, the voltage over this winding is suddenly reduced. So compensation is by Ohm's law, simply using the equivalent impedance here. We can panel beat it a little bit by adding some more, but you can see then we're buggering up maybe the protection. But we do this complements of the supply transformer, but people really, there's limited opportunity for compensation. Now, why would we like to use such a STATCOM? Yeah, to improve voltage regulation, control power factor, and long lines to improve the steady-state power transfer capacity or capability, improve transient stability margins between different areas of transmission, different systems, damping subsynchronous power system oscillations, controlling voltage flicker. But you see, it becomes less attractive when mitigating voltage dips and even magnitude and even unbalance as the upstream impedance. When it changes, the compensation changes. And if we add additional impedance, it requires changes to the protection. But it also increases the total harmonic distortion in voltage, because remember, the load downstream is non-linear, it's controlled. It will suck in the same value of current harmonics, adding some impedance, and what do we have? The voltage distortion goes up. And it's mostly too slow. It normally takes around 2 cycles, and then the load has already stopped making money. So dip compensation requires operation in an overloaded condition, normally when they use a STATCOM, and that is abnormal. You really stress that equipment to help compensate for dips. It can, to some extent, as I've said, but you'll see the solution from Christian and why they have also been awarded during 2017 the prize or the recognition as one of the top 100 innovators in Germany. Was they do it in, let's say, in the time domain immediately. Those compensators takes 1 cycle to go and figure out, and then only thereafter they start compensating, and that's too slow. So let's consider a series solution. It looks like a STATCOM indeed. The difference is the winding sits there, but now you say you just did not like this winding. What is happening here? Don't worry too much. It's only 2% impedance between source and load. No changes needed to protection setting. The secondary side is disconnected during faulted startup conditions. So the moment something goes wrong in the system, this part is short-circuited, first by a thyristor that fires extremely fast, handling huge overcurrents until mechanical lockout kicks in. It doesn't cause any increase in voltage total harmonic distortion, and the equipment here is rated for the compensation and used within design values. No overloading is needed. And it is real fast. 1.4 milliseconds. In the 20 millisecond cycle, the load will not even know anything was wrong. because in 1.4 milliseconds it starts reacting to the change in voltage. So people, there sits our 2% impedance, and it works more or less in this way if you look at dips. It does more than dips. But let's say there sits a dip. This device only adds what is missing, and there is what the load sees. Nothing goes wrong. So, active conditioning of supply voltage. What we achieve now is a continuous conditioning of voltage variation, voltages at the load terminals, and just appreciate this, remains at 1 per unit per phase. This is the perfect world, perfectly balanced between phases, zero voltage unbalance, it's flicker free, compensate voltage sags. Now, no, that doesn't seem too impressive. 40% during as a free phase fault. Most faults are single phase, then it can pushes the voltage up by 60%. Oh yeah, you should have noticed there are no batteries involved here. Very important, no batteries. This is quite useful for me because the phase angle jump is also compensated. Sometimes dips are only classified by means of the reduction in RMS voltage and duration, but phase angle can also change during a dip, which can affect the operation of loads, and that is also compensated. Now, all of this is done very, very fast, 1.4 milliseconds, and this is really where operational risk now gets contained at the terminals where the sensitive loads sit, and the plant owner now takes responsibility for compatibility between supply and load conditions. And people, after the talk this morning, the slides will also be made available. You can have it, you can use it. You don't have to quote even where I have done some of the work. Use it if you find it interesting. I recently even discovered some of my slides in a long presentation someone used in PE. I was quite impressed. But people, this is what we talk about. I have shown you the example of the RMS voltages. That voltage dip that we see here, by adding the missing part, this is where we're working to. Right, now let's look at a quick case study, and I'm nearly finished. Firstly, I have already referred to the financial risk part, where the product can't be recovered because the operation runs 24/7. You can't speed up, ramp up production if we lost some product. But it's also a reputational risk. Promises are made to clients, and it can't be honored, go and buy at the competition. And some losses nowadays I see occur within the wide dip area. And people, it's normally, definitely the high-tech kind of production processes. But you see, the problem is people need high-tech equipment to remain competitive. And more equipment don't really respect where they should be immune against, because if they use that equipment in Europe, nothing goes wrong. It's only here. And it's not only the high-tech industry that suffers. I have seen this example recently that we're dealing with. Diamonds. There are people there in the Free State. They take old diamond heaps. During the days of Cecil John Rhodes, they made lots of heaps there where they so-called took out the diamonds. But they now process it, and this plant is per month producing 4,000 carats of diamonds without mining. It's only taking the mine dump, taking out 4,000 carats per month. But that success sits in this process. X-ray machine, where the moment a diamond comes past here, that machine kicks it out and they collect the 4,000 carats of diamonds here. And you can imagine in that mine, the specific one that I talk about, Johan Rupert holds more than 60% of the shares. But they sit in a rural area, poor quality of electricity. The X-ray machine does not only not operate as I want to, it also fails. And the moment it doesn't operate perfectly as it should, you lost that ability for 4,000 carats per month. But people, even this one, it's not high-tech, no. putting that maize into bags here. I've worked with these cases. It's impressive how they automate this. Huh? Everything runs by itself. Now those are big bags, but you get some of them with small bags. The moment there's a dip, the whole maize flour pouring into the process, pouring into the bags, are bugged up. You clean up the plant, you start it again. Huh? A few times per day. And millipap is needed in this country. Same that you need petrol or diesel. We need millipap. So there's another example. People know. All right, so a difference was made, and I will quickly show you. There is a real case of compensation. Now for a moment, appreciate this. I mean, this looks impressive on RMS, but look here. This is the grid side voltage. Look at the load side. The moment that grid side voltage drops, you can hardly notice at the load terminals. This is the beauty of the solution. Because 1.4 milliseconds fits in there immediately. It is being compensated, and there at the end, some transient, but this is much preferred compared to this. Can you imagine applying this to your UPS system compared to this? Now, okay, the UPS will save a load, hopefully, but during this time, you cycle the batteries and the power electronics. If you take that stress away from the UPS, already the maintenance of the UPS even goes down. The batteries last another few years. Look at the difference being made here in 6 months, the before and after. Appreciate this one. This is how that plant looked like. Now it's how it looks. Those are not dips. It's just indicated as where the voltage ended up. Those extremely unfavorable skin condition being improved. Can you see how it looks now? Those events are no dips anymore. Some of them will remain. I mean, this is not a UPS. Those will remain, but much, much better. Go into a bit more detail here. Before, and already I quote the name, they called this piece of equipment Oscar, and it comes in different sizes. When Oscar is in there, and this is the number of dips against how long the dips are, can you see those remaining are much better than before? The voltages, in terms of residual voltages, this is how deep the voltages was. The voltage retained, the voltage remaining is indicated here. So we can see this one, those ones that are not too deep. Hopefully that is the highest number of dips. But even those ones and those ones have been solved. With Oscar, some of them will remain, but a much preferred situation than before. This one also very interesting, because now, during the day when there's production, you can see those dips with Oscar remaining, sits at the early hours of the morning. This case, when they want to do production, a much improved scenario. This one, the day of the week, this is quite an interesting one. Those bad dips have been shifted, those ones that remains, to the Saturday. So during the week we can do production. A much improved scenario, and counting them now. From a total of 131, those dips remaining now became 6. All right, included in this is dip type Y. So maybe we should only count those ones, but those ones compared to that also looks quite impressive. 2 dips, which would have made the plant stop, compared to 35 in this case. 35. Yeah, 35. All right, much improved. But look what it is doing with voltage. This is in South Africa, where this German equipment is already working. Now, this voltage was not bad. It zoomed in. As you can see, voltage changing from 98 to 102% nearly. This is not bad over a period of time. But look, the moment Oscar kicks in, the load C, 1 per unit voltage all of the time, per phase. So you could have expected what happens with voltage unbalance. It's gone. Huh? Nothing remains. That is most the sweet spot for a motor. They want it. So in conclusion, people, and a little bit of a tongue in the cheek as well there, but users of electricity in South Africa will have to take local control over power quality, conditioning the voltage locally to the level of immunity is needed, and the immunity level realizes in operational risk, becoming money. The National Energy Regulator, also known as NERSA, will not, cannot change the situation, and that what they thought they can do in 2002 is outdated. To enforce minimum standards, they said they're going to do this. That did not happen, and I tell you, it will not happen. Utilities want to do something about it, but they can't do much. If it was not for Eskom, it would have been really bad in this country. Eskom's not that bad. They try, really, to do power quality, for example. And a lot of the utilities try. They try. It's not that they don't care, but they can't do what users expect always. So users will have to budget for taking local control over power quality by means of active voltage conditioning. And Dries has asked me about storage. While I'm here, Dries, what I mean during that part is in the microgrid, which I realize will not fit in here. Local storage, local generation. Even there, I think we will have some application for this, but that's a story for another day. And if DIPs are the concern, then I'm saying using a series STATCOM by the name of Oscar. So, people, you must take responsibility for what is happening to you once you've grown up. And that is where we are. So, if you have any questions, you can, but hopefully we will reserve them for